Hello, in this short video, I'm going to explain the functionality of Unix system calls pipe, close, read, and write, not for low-level I/O, but for inner process communication. Also, I'll show you how fork system call is used to create another process, exec, and wait system calls. So in this short video, I will explain these system calls by creating a shell program. This program would be a simplification of a program similar to the terminal that you're using to run different programs. This shell program only allows you to run one other program. So, but you can, extend it and create your own terminal, create your own shell. So basically, here is what here are the steps that what shell does. The first thing it does, it receives the name and command arguments of a program, or I should say an executable of a program that you want to execute. And then other than that, it may have some option of flag -i, which means that the process that we're going to generate, which is called the child, gets input from the parent. When a process, in this case shell, a program, when you run a program, becomes a process. When a process like shell, in this case, creates a new process using fork, the newly created process is called the child of the existing process. And the existing process is called the parent. So the parent creates a child process. This is it's kind of similar to the multi-threading and pthread create. So the fork would be kind of similar to pthread create. The difference is pthread creates a lightweight process. We call the lightweight process a thread, right? The lightweight process is different from the child process, because when you use fork to create a new process, a new thread, you're basically giving that process a complete access to resources and everything. So the child process and parent process will have like different memory space. They are treated like two separate processes by the operating system. So fork is used for multi-processing, while pthread create was used for multi-threading. Multi-processing and multi-threading are completely different, because the multi-threading, you have like one process with multiple threads, they all share memory. Multi-processing is completely different. You have like multiple processes with their own separate memory space. So, and then their own separate code, right? So this is how this lecture is related to the multi-threading topic, right? Let's get into more details of the shell program. The second step of shell program is it forks the child process. So it creates a new process we call a child. In the third step, in the case of a -i flag, the program has to pass the input from standard input to the child process. And then the next step is the parent waits for the child to run its program and gets terminated. The child will originally run the same program as the parent, but using exec v. You see this exec has an asterisk. It can have like different postfixes or suffixes. So we'll use exec v here. You can use exec l. They're going to be very similar. You can check them out online. And then the last step is the parent prints the child's output on the cd out and exits. Basically, it reports to the user what child did, right? The shell program is very simple. It's just it's a single main function. The includes are in this H file. You see we are using, let's say, this wait or some other, let's say, a macro error for throwing a fatal error, and then some constants and all of that. So we use some includes here, and then the number argument should be at least 2. If it's less than 2, we're going to throw an error, right? And we're going to leave, and that's it. Then if there's a dash I flag, we're going to set the child input integer to 1. And then in that case, we're going to update the argv so that we can handle arguments in a correct way. Then we're going to use two pipes. One is called link to child, one is link from child. These are basically two the arrays of integers. Each one will have like 2 elements. These are called file descriptors. If you may know, like the file descriptors are used to identify file streams, either input stream or output streams, and basically we can use them inside a read or write and also lseek system call to identify the stream. Here, when you call the pipe on an array of size 2 like this, basically you're generating 2 different file descriptors. The first one at index 0 is always input stream. The second one at index 1 is always the output stream. Remember this for the rest of the lecture. So I'm creating a link to child and a link from child. Link to child is used for the parent to send data to the child, and link from child is used by the parent to get data from child, to read data from child. So basically we use the in the parent we use the index 1 of link to child and index 0 of link from child. And if the pipes system calls are unsuccessful, we're gonna have a problem, and we're gonna immediately leave the program. Let me draw a quick diagram just to show you how things look like. So let's say this is the parent process, and this is the child process. We're going to generate 2 pipes. This is one of them. This is another one of them. And then let me use a red color to show you. Basically, we're going to send data from parent to child in one of them, and we're going to receive data from child. We're going to receive data from child in the parent. And the names are clear. Basically, the link to child is this one. The link from child is this one, right? So that's what's going on. And then that's it. So after we'll come back to this, we can configure this more. But after doing that, it's time to clear all the drawings. We're gonna do this. We're gonna create we're gonna call the fork system call. The system call is going to generate a new process, and it's going to return an integer PID. PID would be an unsigned integer. Basically, that would be the ID of the child process. So it's going to return the ID of the child process to the parent. After fork, then we're going to have 2 separate processes, the parent and the child. What Unix does is it copies or duplicates the parent's code into the child code. So surprisingly, the child is going to run the same exact code that I'm showing you on this screen, which is going to be the main function, the shell program, right? However, there would be a small difference. The difference is in the parent process, PID is a positive number, which is the real ID of the child. For the child process, the ID is going to be 0, so we're going to get to this else part. So let me say that again. Fork is going to duplicate the process, the code, and it's going to create a new child process. The child process will later replace the text section with its own code. So I'll get back to this later. What are we doing in the parent process? We're going to close the end of the link that we don't use. The link to child is used for writing data. So the read end at index 0 should be closed. We're going to close the write port or the write end of the link from child in the parent, because we're not going to use it. we're going to create some space for the input and some space for the IPC buffer. This is used to store inputs and then pass it to the child. This used to receive, to basically accumulate data that is coming from child. And then we're going to use this to print it on the screen. If the child input is set to 1, what we're going to do is we're going to start reading data from standard input using getchar, and then store it in the input, and then we're going to write this into the pipe linked to child, so the child knows what data the user has input, so that the child can react appropriately. So that's how you send data through a pipe, right? Using the write, remember the write, for those of you who are not familiar with write is a system call that gets a file descriptor at the beginning, a buffer, and then the number of bytes that you want to pass. And then that's how it transfers data. And then after that, we're going to close the link to child at index 1 because we are done writing. So this is going to flush data out, and the child is going to eventually receive that. And then we're going to read the data from child in the other link, from the link from child at index 0. That would be the file descriptor. What we're going to read is going to be stored in the buffer, IPC buffer, in a process communication buffer. And then the buffer size is, in this case, like 4 kilobyte, 4 kibibyte, 4096 byte. And then if the read is going to return the number of bytes that have been successfully written. If it's -1, something went wrong. Otherwise, we're going to set the last byte of the IPC buff, which is used to 0, so that we know that like this buffer is a string, because the string always ends at 0. And then the parent waits for the child to be terminated. Wait null is kind of similar to the join in multi-threading. In multiprocessing, we call it wait, not join. And then at the end, it's going to print out the data received from child. Whatever is in IPC buff will be printed. In the child process, we're going to do the opposite. If PID is not positive, it's going to be 0. So that means this code is run by the child process. The child process does this. It's going to close the other end of link from child and link to child pipes. So the child doesn't use the read end of link from child because child wants to write in it. So it's going to close that. Child doesn't use the link to child at index 1. It's going to close that because the child uses this to read data, not write data. So we're going to close the output stream part of this link. And then it's going to connect the standard input to the link to child at index 0. So basically, child redirects its standard input to the first file descriptor of link to child. This way, whenever the child says, for example, get char, it's not going to get a char from the keyboard. It's going to get a char from the parent, from this link to child, which is connected to the parent. And then the other one is a link from child std out file number. That's going to be this duplicate or dup2 is going to redirect the child standard output to the second file descriptor of the link from child, which is this one. So from now on, when the child says printf, it's not gonna print on the screen. It's gonna send data to the parent, and the parent may print them all at once at the end of the program. And then after doing that, we're going to close these links because we have used them to redirect input and output, so we don't need them. That's it. And then exec v is the last line that the child will run in this code. The exec v basically replaces the code section or the text section of child with its with a new executable. The executable was passed as an argument of this program, And as I told you, the command and arguments of the child is going to be given right after the name of the child. So this is the name of the executable. These are the command and arguments, or the list of command and arguments for the child. So exec v receives two data. One is the executable name and path possibly, and the second one is going to be all the command and arguments that the child needs to run the program. So after this, if we still continue running these lines, that means the exec v has failed. In that case, we're going to say fail to run the child process with the given arguments. And then we're going to end the child process as well. And that's it. That's the end of the program. Let's run it. Let me, I have some. All right. So I have a party open here. What I'm going to do is I'm going to say, let's compile this. I have already done the compilations for your attention. gcc-o shell.c-i.-w. That's going to compile it, and then I'm going to run it. How do you run it? Let's run it in different locations, with different command and arguments. One is, let's run the actual ls function. You know what ls program does? It's going to list all the files in a parent directory. So let's do that. I will say shell, and this is the location and the command line, the location and the name of the executable of ls, which lists all the files. So when I run this, it says the shell program has created that ls program. And here is the list of all the files that you see in this directory. As you see, I have a two lower program. Let me show you the code chat It's going to just lower the case of any characters received from input, and it prints on the output. So it's not going to do anything special. What I'm going to do is I'm going to run this to lower executable using my shell program, but I use -i because I'm going to give it input. Then the shell says, give me the input for the to lower. And I say, okay, let's do this. Hi words, and then by wall, right? It's going to lower the cases of H, W, B, and W. So let's find out. I'm going to press Control D. That's to end the current input stream. And the output of the to lower is correct, right? It's going to lower the cases. So we have seen a successful communication between the parent and child. The next try is trying the being grep. Grep is a function that finds a character or a word in text. So after it finds the text, it's going to print the line that contains that word. So in this case, I'm saying, let's run the grep for hi. That means I'm looking for the keyword hi, H-I, right? And then it says, give me the input. And I say, all right, this will be printed. This is my prediction, because the word this, T-H-I-S, has H-I. So it's going to print it. And then I will say, this will not, because this one not going to print it because grep is case sensitive though. So the HI is uppercase, so it cannot catch that. And then I will print hi word, and then by word. So the hi word will be printed, the by word will not be printed. And then Control D and this stream. As you see, the grep has printed only the lines that contain the word hi, only these two and nothing else. So with that short demo, we're going to end this meeting. Thank you.